Hi, welcome to this video that is for students who are able to run the Einstein rocket applets for the Black Hole Lab. And this may be most of you because it is a kind of older program that takes a little finesse because it is an older Java applet. I'm able to run it under kind of the Internet Explorer, but I have to go and kind of put exceptions for the individual web pages within the Java control panel to allow it to run. Usually this thing like here will be blocked in Chrome or Firefox. But I'll be recording, kind of going through the steps of this section for the lab, and that way you can do it on your own with just watching the video. Now, what this applets are designed to do is kind of illustrate a few things about relativity, in particular kind of problems of time dilation and length contraction. And hopefully if you've gone through the videos or done the reading on special and general relativity, what you find is if you have this concept of the speed of light being a constant, regardless of the emitter's motion or observer's motion, that breaks with Newtonian mechanics. And with that, if only the speed is kind of an absolute, that means two positions can't measure the exact same time and amount of length. Their perceptions of time and distance or space will be different. And kind of illustrate that, there's a few thought experiments and a few kind of interactives with this Einstein's rocket website. But again, unfortunately, because it's a bit older, it's becoming less and less compatible with newer browsers and computers. But with that, I'll go through these steps. Okay, so we're going to go through the first 5 tutorials that are on the thought experiment. Okay, so each one is kind of listed here. How long is the second? That second, the shrinking ruler, spontaneous events, time-space diagram, and then space billiards. And to illustrate that, again, kind of having kind of a light move between two positions is kind of a good way to illustrate that change. So right here, again, a simple clock made by having light pulse travel between two mirrors. Okay, so now you're going to move the clock at a good fraction, about half the speed of light. Okay, and with that, if you have the moving reference, that passage of time is slower compared to our timing at the rest frame. You can see here the actual path is now longer, and with it light moving the same speed, it's going to take longer to actually cover that distance from our apparent point of view. And that observed kind of difference in distance that the light pulse traveled compared to if you were moving with it or from the rest frame is where you can kind of derive this factor of gamma, which kind of illustrates both the difference in time and difference in kind of measured length. And it's equal to 1 over the square root of 1 minus the square of the velocity divided by the speed of light. Now, later on in the lab, there's a couple questions about calculating that out using this equation, that gamma. You don't have to plug in for C. If you just have just kind of the value, say 0.4 C divided by C, that C portion just cancels out. In that case, you just be squaring the 0.4 within that part of the equation. So here I'm going to type 1 in. So that is a very slow compared to the speed of light, so the gamma effect is very small. And I'm going to try with 7 now. Okay, so this is even more extreme gamma. So as you'll see in the lecture, you can increase the speed of an object, but it essentially only asymptotically reaches toward the speed of light, and your gamma gets larger and larger, and you have a bigger effect of this kind of time dilation or length contraction. Now, with that forward motion, the pulses are no longer in sync. Okay, so again, I'll try to start with the 1, and then I'll do a 7. So something that's moving very slow compared to the speed of light, it's effectively almost Newtonian. On the other hand, if you're a sizable fraction, it really becomes noticeable if you start becoming 40% the speed of light or higher. Okay, at 1. And 7. Now, with the space-time diagram here, the main points is because of that effect of relativity, the point where on the time diagram that a light pulse reaches an end of the rocket is no longer the same. If we had very, very slow, both these positions would be the same. They'd be reaching the ends of the rocket at the same time, but with the effects of relativity, in that case, that's no longer the case. Okay, and again, let's try with the lowest and then the highest. So again, there's not that much difference if you have a very, very slow speed, at least compared to the speed of light. And let's try with 7. Yeah, in that case, it wasn't even enough time for it to reach the end of the rocket. Let's try a little slower here. Let's try 3. There we go. Yeah, so E with momentum, which Newtonian again is just mass times velocity of a moving object, that has to be corrected for the effects of relativity. Okay, so here's 1. 3, and the most extreme 7. Okay, so now we're going to go to the 1D space rally, so we actually can see the difference between time for a given gamma. And for this one, we're trying to find the gamma for moving at 4C, 8C, and 9C. So you can actually calculate that yourself, again, just by plugging into the time dilation equation that's on the paper. And then what I'm going to do is actually accelerate that. So let's do that myself here. All right, so for the first one, hopefully you got something around 109, your own calculation. So let's see if I can get that up to 109. That's close enough. All right, so you can see how steep the slope is. So there's some time dilation. There's a difference when the pulses are reaching each end of the rocket. So as the gamma increases, we should see that larger displacement, meaning time is further slowed down due to the faster speed. So our next one is 0.8. Okay, so I'm getting a gamma of around 1.67. Let's try that out. That's close enough. As you can see here, as we expected, a much more steeper slope and a bigger difference between the rocket and Earth time. And the last one is a 0.9 the speed of light. Okay, so all right, so I'm getting a gamma of 2.29. Not sure how close I can get here, so let's see. Let's try that again. So in this case, there's even a bigger difference. The time is moving really that amount of time slower for that rocket compared to the person at rest. Okay, so next thing is just this little activity. So a difference in time. We traveled out and back with the Newtonian versus Einstein. So I'm going to do, let's see, I'm going to try round trip here. Okay, so for Newtonian space, the clock, as you can see here, I'm sorry, Einstein, as I accelerate high enough, there is a difference in the amount of time viewed in the rocket compared to on Earth, especially if I accelerate there. And this one, this little game is using kind of, again, how in space there's no friction. So the only way for me to slow down is actually to turn my rocket around and put exhaust the other way. Yeah, made it back to Earth. Okay, so in this case, between my accelerations, you have that difference in time. Well, let's go back. Let me hit this again. Let's do a Newtonian. Come on. And if Newton's laws were fully in effect, doesn't matter. You could do any acceleration. There'd be no time difference because in Newtonian physics is an absolute reference frame of time and space. But as we'll see in the next couple lessons how this is incorrect. And even though many of these ideas from relativity are strange, over the 20th century, many experiments have been done to illustrate that both special and general relativity are correct. So, Newtonian, there would not be a time difference, but under Einstein's rules, his corrections, there is. So with that, to make some interesting things, if we can accelerate a ship fast enough, even though nearest stars are several light years away, if you could accelerate a ship fast enough, that distance would contract from the point of view of the rocket, and in that case, that would be possible to actually get someone to another system within a human lifetime, regardless if they're moving fast enough. Now, of course, this would be a one-way trip because time would be so slow for the people on the rocket that decades to hundreds of years would have passed for people on Earth.
Daddy, where's D?
That's letter D, sweetie. I'm still recording. Hold on. Okay, to kind of show an example here. Here's under Einstein physics. No. Doesn't really give you a lot of space to accelerate too much. But the faster you can go, the higher the gamma, the bigger the time dilation. Okay, so I think that covers this portion here. The next set actually fully allows you to look at black holes. So that one goes to the Hubble website. Which should not be a problem for, we go there, for most things. But if you have any questions, please let me know. Let's see here. Uh-oh. Do you update the website? Let me see. Okay. If that link doesn't work for you for the black hole, it looks like they might slightly changed it. Yeah, instead of Hubble site, I'm sorry, it's Hubble stsci.edu, explore astronomy, and then black holes home. So try entering that instead, and that will take you to beginning here.
Black holes are out there, but what are they? The mass of the Earth.
Okay, so that should be a correction there. I'm gonna probably actually maybe just fix that right now and update that on the website. So those of you doing later won't have that issue. All right. Regardless, thank you for watching, and if you have any questions, please let me know. The next day or so, or when I hopefully get a chance, I'll have the first lecture on relativity, and then start of next week we'll have a fuller lecture on black holes.